Okay, I thought originally wasn't going to do a video on this, but I thought, oh, what the heck, why not? A lot of people probably haven't seen one of these before. It's one of B&K Precision's. It's not that it's rare, but it's rarer, I guess you could say, than a lot of the other multimeters they made over the years. So this is the Model 290. It is not a vacuum tube voltmeter. It is actually, as it says on the meter there itself, it's an electronic multimeter. So it's 100% solid state. No tubes inside. But, like a vacuum tube voltmeter, it has a high input impedance. I'll describe that a little bit, but I won't get into great detail about that because there's lots of good videos on YouTube done by other people, and I may even do one specifically on the subject showing it. But input impedance is important when you're taking measurements. Now, a lot of times when you're troubleshooting a circuit, you just want to get a general idea. Is there voltage or isn't there? You really don't need to be accurate. But if you're checking stage gain and you need to know exactly how many volts are on a vacuum tube or on a semiconductor, a transistor, or an FET or something, the loading effect of your multimeter can affect your measurement. So when you look at a schematic for, let's say, a radio, mainly what I work on here, a lot of times they'll have either voltages written on the schematic at, let's say on a transistor for the base emitter and the collector, or, in a vacuum tube, it'll have the anode, the cathodes, grids, screen, but it'll have voltages on the schematic. And if you look in the legend on the schematic, it will tell you what the input impedance of the multimeter that was used to take those measurements. Now, if you use a multimeter that doesn't have exactly the same input impedance, your readings may be different. They may not, but they, by the same token, may very well be different. So just be aware of that. This multimeter has, in DC, has a 15 mega ohm input impedance. 100 kilo ohms of that is in the probe. So when you're taking DC voltage measurements, you flip this little switch forward, and that adds 100K, so it's actually 14.9 meg of impedance in the meter, and then there's an additional 100K inside this probe. And then when you're taking AC voltage measurements, you put it in a direct position that removes the 100K resistor out of series. So on when you're taking AC measurements, it's 14.9 mega ohm. But that's just something to be aware. Like I say, there's good videos that actually show that. I think Vern over at the Radio Mechanic, I think he did one where he actually showed. He took different multimeters that have, some of them are like, like maybe 10K ohms per volt. There's multimeters, a lot of your standard vacuum tube multimeters back in the day were 11 mega ohms. And if you look at schematics for old electronics, a lot of times that's what they're going to specify. Or it could be different, like I say, but it's just something to be aware of. Now, I like these multimeters. I think I know it's at least my second, it might be my third. I'm thinking, and I'm pretty sure this is my third. And I've worked on a few of these before for other people. They're really nice meters. They have some advantages. Now, a lot of people are thinking, well, Mike, you got a fancy multimeter right there. That's a 5.5-digit meter. That thing is just orders of magnitude more accurate than this meter. Well, you're not wrong. That it is. It does have orders of, several decimal places better accuracy than something like this. But honestly, nothing beats a needle, especially if you're peaking a circuit. IF transformers or something, you just can't beat an analog needle. Trying to peak, with an alignment tool, you're trying to peak a circuit. Trying to do that with a digital display, yeah, that's a pain in the hoo-ha. Analog meter, you can see the needle comes up and it starts to come back, and you can adjust for that peak. Now this one has, this will measure up to 1,500 volts DC or 4,200 ohms. Let me try that again. 4,200 volts peak to peak in AC. Has a fairly high resistance range too. It has, well, actually, it's about the same as you'd find for most meters like this, but some digital multimeters can't read extremely high resistance. Where this one, and like most meters like this, your older analog meters, they'll have a R times 1 meg scale. So, that's 1 meg times whatever the ohm scale they're reading. This one goes up to 500, actually out to infinity, but, and the farther you get up this scale, the more it compresses, but you could easily read up to 500 mega ohms with this meter. Like I say, a lot of digital multimeters won't do that. One nice thing if you're working on circuits, a lot of times you need to measure a positive or a negative voltage. Well, with this meter, it actually has, you can change the polarity of your probe. So, when you're taking a DC voltage measurement, if you stick it in the DC positive, that makes this your ground and your probe is your positive. But you can also flip it to minus DC volts. That makes this your positive and your actual probe is now the negative. Let's see, this does also have a built-in amp meter. I usually don't use meters like this for the amp meter function. I'll usually use a digital meter. Mainly I'm using stuff like this for, like I say, the voltmeters or the ohm meter. Now the nice thing about this meter is it has several scales that you won't find on several other meters. For starters, it has a dB scale. It also has just a centering scale. So, if you're, again, maybe you're trying to peak a circuit, or maybe you're trying to balance a circuit, where you want exactly the same amount of positive voltage and negative voltage. So maybe, let's say like a left and a right channel in a stereo or something. You're trying to get a balanced voltage. What you can do is you can put this meter into the DC ohms position. You would put it to the highest voltage range. You'd attach your meter probes into the circuit. And basically what you do is you start, and you'll turn the 0 knob to get the needle. So instead of being 0 down here, you'd 0 it on the 0 of this bottom scale. And then you start turning your range down, because you don't want to slam your needle against the right side. That's why you start out with the voltage range up the whole way. But you'll slowly start turning that range down until you get the needle to where it's in this scale here. And then you can switch, let's say in a stereo, you could check from left channel to right channel and see if it has an even balance of voltage, or, positive and negative voltage in whatever circuit you might be working on. The dB scale's handy, and manual actually has the graphs in it. So there's actually a correction factor, because this scale, as you can see, 0 dB is equal to 1 milliwatt across 600 ohms. So if you're measuring anything like, let's say, a speaker in a CB radio, and it's an 8 ohm system, so your speaker system, well, this is not going to give you an accurate dB scale, because this is calibrated at 600 ohms. That's where you would use your calibration factor here. And it's real easy. Here's your meter correction over here, either plus or minus. And then here's the impedance in ohms down here. And you can see it's logarithmic. But so, here's 10, so you'd come back 2 lines, 10, 9, 8. You'd follow that up. And, I pull it up here pretty close and look at it. Let's see, 8 ohms would be 19, so it would be plus 19. So whatever you read on that dB scale, you would need to add 19 dB to that. But that would be an accurate reading on an 8 ohm load, because you've corrected from 600 ohms down to 8 ohms. Also has for your RMS volts, for your AC volts, has correction factors for that for difference. You can see there's 600, 50, 16, 8, and 4 ohm. So when you're taking AC voltage measurements, also has correction factors for that. Like I say, it's just nice to have that. A lot of meters don't have a dB scale. They also don't have a 0 center scale. One of the really nice features of this multimeter is it has it has several ohms ranges over here, but it has 2 ohms positions. There's a high ohm. I'm going to tilt the meter up, get a little bit more light on it there so you can see it. There, you can see it says high ohm and low power, or high power ohm and low power ohms. So that's an extremely handy feature. Now, what that does is if you're testing in a circuit, so you want to test a component in circuit without removing it from circuit. Well, in an ohm meter, the way that works is it's applying a voltage through your probe. And it's measuring how much, it's measuring the drop. It's basically a bridge circuit. And that unknown is what's being read on your meter then. But the problem with that is most ohm meters will turn on semiconductors because the voltage is too high. This one has this low power ohms. When you put this in the low power ohms position, there's only 0.033 volts or 33 millivolts on this probe tip right here. That's not enough to turn on germanium or silicon, semiconductors. So you can test resistance in a circuit without having semiconductors turn on, because most multimeters well, anything, that one, even meters like this that don't have a low power ohms function will turn on diodes, because the voltage that's at the probe on these is enough to overcome the forward bias on most semiconductors. So with this, you could measure in circuit, actually measure the resistance of a component, let's say a resistor. So, let's say there's a diode, a resistor, and a diode, and you want to measure and see what the actual resistance is of that resistor. Well, with a normal ohm meter, the problem with that is when you attach that ohm meter in circuit, it may forward bias that diode, which may give you an erroneous reading. Well, in the low power range here, there's not enough voltage potential at the tip of this to turn on that diode. Where if you turn it into the high power range, it does have enough to turn that on. So we can actually demonstrate that. I just pulled out a block of resistors here, just small signal diodes. So here's a diode, and I'll keep it in the same orientation the whole time. We're going to have anode on the left, cathode on the right. So let's put this in the low power ohms position. Actually, the first thing to do, we want to make sure we have our meter set up here. And it may look out in the camera, because you have to remember, an analog meter, unless you're viewing it straight on, you can get parallax because the needle's not touching the face. So, when you're looking down at an angle, that's always something to be aware of with multimeters like this. And it's actually why this has a mirrored scale. That mirrored line there, doesn't matter how you look at this meter, the line that mirror is reflecting, actually, because you can see that. You can see the needle, and then you can see a little black line right above it. No matter what angle you look at it, it's always going to be at the same exact spot on the mirror. But when you look at the needle from different angles, it's going to look like it's on zero, it's not on zero, it'll switch because of the parallax, just because of that range that it's away from it. But in any case, we'll get her zeroed here. And then disconnect the clips. We're going to set this for infinity, so the infinity logo right there. It's good right there. And now, like I say, we have it in the low power range. We'll connect the ground clip to the anode, probe tip to the cathode, and you can see nothing. And then if I switch, and like I say, I'm just going to leave the diode in the same orientation all the time. We'll switch around here. Now, this would normally turn a diode on, taking a normal ohm meter and applying your probe tip to the anode and your ground clip to the cathode. But you can see, nothing happened. No needle deflection. Now, if we put it in high power ohms, ground clip still attached to the cathode or the negative, and we attach the probe here, aha! Because now, since we put it in the high power, and this meter is like most other multimeters, it's going to have over a volt. I think this one's around like 1 1/4. I think that's what it is like 1.25 volts on this probe when it's in the high power ohms position. But that's enough to forward bias this diode and turn it on. And then, of course, we can see if we connect the other direction, because we're reverse biased, the diode, again, it's turned off. But like I say, that's a handy feature. So, that just shows that in the low power ohms position, there's not enough voltage to turn on a semiconductor like this. So you can take accurate resistance measurements in a circuit with no fear of turning on a transistor, an FET, even integrated circuits and the like. And actually, you can actually measure. Now, it might be not so much with modern microprocessors; they're so advanced. But back in the day with a meter like this, with the technology of the time, with old CMOS and TTL style ICs, you could actually measure the resistors inside of the IC with this meter because of that low power ohms function. You could take your meter, you could measure the internal resistor inside the IC, and then that would measure the resistor, and then you could check, let's say it's a transistor, because you've got to remember, integrated circuits can have tens, hundreds, thousands, or today into the millions of semiconductors are actually inside of one integrated circuit. But you know, the older, like I say, TTL and CMOS stuff, a lot of times all they are, it's just transistors. It's just lots of little transistors in there. But they were very simple. So you could check the resistance of the internal resistor. So if you had fear of something you were working on might have had an overvoltage situation, the IC's working, but you're not sure if it might have got partially damaged. It maybe got hot. Well, you could actually check the resistors inside the IC with this low power ohms function. You could check the resistance on each of those internal dropping resistors inside the IC, and then you could turn it to the high power position, and then you could actually turn on each of those semiconductors, just like we did with the diode. You could, check forward and reverse bias and see if those semiconductors are actually turning on. But like I said, that's a really handy feature. It's not something you use a lot, but when you need it, there's no substitute. So, now this meter, I got it used. I wasn't sure, other than I knew the seller told me the needle moves. Other than that, he really didn't know. He said, I plugged it in, went like that, and I had it in that high power horseshoe thing, meaning the omega symbol or the ohms logo. He didn't know what that was. But he said, and the needle bounced around, so that's all I cared about. As long as the meter movement was okay, really nothing else I can't fix inside of this thing. I can even replace the wafer switches in here if I had to. So I replaced the electrolytic capacitors. Like I said, I've got a couple of these. This one looked in decent condition. More importantly it came with the original B&K probe, the original Dynascan probe. You can see it says Dynascan on there, PR21. And came with the manual. Even has the original warranty. I mean, wouldn't B&K get a laugh if I mailed that thing in, considering this thing was probably, 1970 something? Is there a date? Don't see a publication date anywhere here, and I can't say that I really took note of the date that was on any of the capacitors that I replaced. But in any case, it came with all the original paperwork to include the parts list and the schematic. Now, the first thing I noticed was when I opened up this schematic. Now, anything that's highlighted in yellow, I did that. That's all the adjustment or the calibration points in this. But the first thing I noticed was, somebody had highlighted with a blue pen and a red pen a bunch of stuff. So, somebody's been troubleshooting something. Not a good sign. So I looked the meter over. I couldn't find anything that looked like it had ever been changed. Everything looked original. So I recapped it. Like I say, replaced all the aluminum electrolytic capacitors. There's only like 2 or 3 tantalums in there. Just to be sure. I just went ahead and replaced those as well. Fired it up. And the calibration procedure is also in the owner's manual here. Went through the calibration. Matter of fact, right there, calibration. Shows all the calibration trimmers right there. And I go get the whole way. I'm like, oh man, this thing's going to pass with flying colors. The absolute last thing you calibrate is the high ohms position. That position right there that we were just using. I get to the high ohms function, and I can't get it to calibrate. I get to R1, I turn that calibration trimmer, the needle, it's not cooperating. There's no other way to say it than, something has seriously gone wrong in this circuit. And it was obvious it was that trimmer resistor, just because of how erratic it was. I could just tap the resistor, and the needle would bounce around, or it wouldn't do anything. So, I pull out the parts list, and I'm like, no biggie. I have pretty much every trimmer resistor known to man. I've got every size, shape, format, lead configuration, and value there is. I've got them all. Well, I stand corrected. There's one that I don't have, and it was the one that I needed. This has I have every single trimmer resistor in the same size, format, everything that's in here, except for one, and that was R1. 5 mega ohm. Yeah, that's not exactly a trimmer resistor size you see very often. I've got 15K, 100 ohm, 100 ohm, 1K. I've got the 500K, the 20, and the 50K trim pots. I did not have a 5 mega ohm trim pot. I was like, you've got to be kidding. So, and of course that's an odd value, and it's a really large size. So I ended up getting actually the wrong size. Now this is the right format. It's a, the type that's meant to stand up. As you can see, they stand up proud off the boards. They're really big ones. Actually, I can just turn around here in one of my drawers and pull out. Show you what. Let's see here. That's the wrong drawer. That's all the smaller sizes. Actually, they were all out in the other room in another parts cabinet. But anyhow, the only thing I could get in 5 mega ohm that was in this format that stands up off the board like this, doesn't have the 90-degree leads, was the smaller format. So the leads are a little bit too close together. So I couldn't stick this trimmer resistor back. It's actually this one right here. It's the third one in. And it's actually, it even says down, recessed control. It's way down there. So what I did was I just took it off. The solder pads that trimmer resistor actually soldered to were, of course, had some meat to them on the outside edge of the hole. So I was able to just tack the new trimmer resistor on this side of the circuit board, or the back of the meter. As soon as I got that in there, turned it on, went right to low ohms, zeroed it, disconnect the probe, you go to infinity, adjust your ohms control here for infinity, and then all you're supposed to do is flip it to high power ohms, and then you adjust that R1 so it also reads on infinity, and it came right into calibration, so... But yeah, I was like, of all the things, the absolute only part in this thing I didn't have in stock was the one part that was bad. That is just my luck. So, yeah, I actually had to wait a few weeks, because these actually came from Bulgaria. They're made in Spain. They're, what is it, Pyre, I'm not sure how you say it. The P-I-H-E-R. They're good, high-quality trimmer resistors, but they're made in Spain, like I said. But yeah, actually, the seller I found that had these is actually in Bulgaria, so yeah, it took a few weeks for those to get here. But so there, I've got a good calibrated BK Precision Model 290 now. Like I say, it's nice that it came with the original probe. I got a couple of these, and like I say, the one thing a lot of times you'll find that goes bad with these probes is, you see that? It's all one piece molded, this cable. This is shielded. They do that for a reason. That way you don't have to worry about AC, especially because this will take AC voltage measurements on, at higher frequencies. And you don't want stuff leaching in through your cable. So this is a shielded cable. And a lot of times what you'll find is this cable over time, just from people abusing their meters and dropping stuff. This is plugged in the front there and dropping stuff on it. The braid will eventually, this outer jacket will crack and the braid breaks, and yeah, it just becomes a mess. But yeah, this one, like I say, really nice. It's a little stiff, to be expected. This is probably about as good a condition, honestly, as they come in. It's a little stiff, and these things were actually a little bit stiff out of the box when they were brand new back in the day. But yeah, like I say, it was just nice to see it came with a really good condition probe. So there you go. Oh, one last thing before I forget. If you own one of these, and you turn it on, the light doesn't come on, and the meter doesn't do anything. It's just completely dead. Don't panic. It may just be a bad light bulb. Apparently this meter came in 2 different configurations. I have seen people that have commented on this that they didn't know, they thought somebody had tinkered with something. Now, like I say, the meter's together, you can't see it, but this is a light bulb, an actual incandescent light bulb in there. It is attached. The wire, one wire goes down to the circuit board, and then the other wire goes to a resistor that's just hanging up off the board. It's a 120 ohm resistor, and then that resistor goes down to the board. Well, if you look at the silk screening on the board, the silk screening just shows the resistor attached to the board, but it's not. It has a light bulb in series with that resistor is what they've done. And it's a modification, but it's a factory modification. And if we grab the schematic here, I can actually show that. Now, I have personally never seen one This meter apparently came in two configurations, like this, with an incandescent light bulb with that modification, or the way the schematic actually shows it, that should be an LED, because there's a transistor in here that would control the LED. Well, that's not LED. So what we have, let me get a pointer here. This resistor right here. So you can see here's our transformer, you can see here's our rectification, our filter capacitors, and there's a resistor, this R60. It's a 100 ohm, 10%, 1 ohm resistor. But you can also see there's two asterisks right there. Well, if you look down here, asterisks, it says CSA units use instead of R60 and D6 LED, and D6 LEDs right here. LED is deleted. So what they use is this circuit, which is what's in this meter. And what they have is a 120 ohm 1 watt resistor with a 2 volt light bulb in series. So basically that resistor and light bulb are in series here. Now I kind of get the feeling the reason they did that was it's a current limiting circuit. If you work on old radios and televisions, I'm sure you know what a dim bulb tester is. I'm not going to go into great details on that. Pretty much anybody that works on old stuff has a dim bulb tester. I've got one. It's nothing more than a bunch of light bulbs, literally, like you screw into your ceiling. But they're used to limit current going into something. And you can control how much current's being limited by what wattage light bulb you use. Like I say, you can look on YouTube. There's, good Lord, posts all over online. You can see what I mean. But basically, that's what this light bulb, I think that's why they have. It was a CSA, but like I say, I've never seen it with an LED. So I get the feeling this was the original design. CSA wanted it with the light bulb. That's the way they wrote the schematic, but when it actually came to producing these things, I think the only thing they ever used was the resistor and light bulb. But like I say, what that does is that limits the current, that light bulb. So if there's a dead short, let's say right here, at this junction, or even at this Zener diode, or this, electrolytic capacitor, let's say it was just, that's actually a good example, because that could happen in the real world, and commonly would. An electrolytic capacitor shorts out. Well, if this electrolytic capacitor shorted to ground right here, the meter wouldn't blow up. You wouldn't burn out your transformer, because this light bulb right there is in circuit. It's limiting the current, so it's no more. It can't let any more power through than the normal power you'd see going across that light bulb. So I think that's why they did it. I may be wrong, but that seems to be the most logical reason that I can come up with is why they had it. They probably decided, we just won't use the light bulb. We'll go with what CSA contract had specified for their meters, and they just used that and everything. But I know a lot of people that have had these meters, thought they were broken, got rid of them, sold them, gave them to somebody, and eventually somebody figured out, well, hell, all it is, the light bulb's burned out. Because if that bulb burns out, you just disconnected your power supply, because there's the transformer, diode. Well, if you break the circuit right here, you just broke the circuit for the your secondaries right here. Like I say, there's your rectification and your filter cap. So yeah, you break the circuit, the meter's not going to come on. So just something to be aware of. Light bulb doesn't come on, the meter doesn't do anything at all. First thing you should check is see if it has an LED, which I've never seen, or a light bulb, every one that I've seen, and see if the light bulb's good. If it's not, just stick a new light bulb in there, and your meter very likely will come back to life.